Good morning. Dobre utro, hope I say it right this time. Welcome to my talk about managing high load and low budget. So this talk will consist of a few segments. One will be about the problem of what the problem is we're trying to solve, why we're trying to solve it, and then we'll dive into how we solve it with technology. Right, so without further ado, just to talk about the high load aspect of things. So I've been involved in the payments industry for quite some time, so over 10 years I've been building a payment system there around then. And what seems to be the common problem with these payment systems, as they are all, when it comes to integration and testing, they're very cumbersome. So what we try to do here is to help that testing and integration phase to be much better from the developers' point of view, from the technology team's point of view. And what we did there is we built a product totally bootstrapped. There's no investment involved. And when you build something from your own money, budget becomes very apparent that you have to watch out for those budgets and make sure you're in within budgets. And what's the reason for payment stuff is very simple. Payments usually are broken in most of the companies. There's always an issue when you try to pay for something online with your card. There's always something going wrong. You're mistyped your CVV or your security number in the bank, or there's random errors showing up to say the bad thing happened. And it all can be avoided very simply by having better integration. Your tools are limited. You're limited to the tools that these providers give you, which can be APIs that are very rarely available, for example. So they're very, very bad test tools that you've been given, right? And what we're trying to do here is a very generic sandbox that can handle thousands of requests per second from any angle coming in and provide a much better service with these sandboxes. When I talk about what's wrong with Segment 6, for example, this payment test system is not available. I worked with a company recently where the test system was always only available on Fridays between 4 and 6 p.m., never before, so it's not acceptable if you're trying to integrate there. They're never same as the real APIs, which means there's always some differences between them when it comes to the test API and the real API, and they always we've been restricted with 5 to 10 test card numbers and very simple cases, but not really the nitty-gritty cases that people encounter in everyday scenarios. Okay, and what we choose to do there is try to fix the problem. And that's when we delve into what we did. So what we did is we prototyped a system, essentially a mocking system we can call externally. We did it in a couple of companies, did everything in-house, but it comes to a price as well. You have to maintain these systems, you have to spend time and money from your developers' time and money in order to keep it up with the changing APIs and whatnot. But then we decided to turn this into a product ourselves, so we took upon ourselves, spent about a year and a half of our own spare time to build this product. And the first step was we wanted to build a prototype. We wanted to make sure that we can provide a service which can withstand, change in loads, change in traffic, number of requests coming in, making sure the service is not brittle. It's a very steady service that can help many people with these integrations. So in terms of technologies, we've gone for the niche. Or slightly niche, we chose Erlang and Elixir due to purpose endurance of these languages, endurance of these ecosystems. So usually people would choose more, I would say, regular things in the payments industry. Some might choose .NET, some might choose Java kind of systems to do these things. We've gone the opposite. We've gone the hipster way and choose something that it's not so common. But bear in mind that Erlang and Elixir has been out there for a long time. So Erlang has been there for more than 30 years. Elixir is fairly new, but it's built on top of that Erlang ecosystem. So it can withstand a lot of traffic, withstand a lot of trouble, and still serve out the API requests to the customers at ease. The very basic stuff we wanted to do with our applications that were simple. We wanted to make sure that you can configure these APIs, these test APIs, these simulations, in terms of, for example, network issues, so you can configure latency, you can configure package loss, you can validate your requests coming in and out very quickly, and we wanted to measure how many requests you send in per second, how many requests you send in per month, and then so on and so on. Okay, and we set ourselves a very, very low goal of the average response time between that has to be around 200 milliseconds. So this is what we started doing. This is a very simple early node. You might see, I'm going to talk about supervisors later in terms of what they mean and the web workers. But essentially what it was, it's a single process that accepted incoming requests from all around the world. Right? And it served us well. It worked well for us in the very early days, no problem. And we proved that we can do this very, very simple system. We can do this very simple system, and again, within budgets, our budget was zero at the time. We wanted to make sure we can run it in any free instance available that it's up to us. So we tried out everything when we were doing this. We did it in a wholly Heroku instance, ran perfectly fine. AWS micro instances, fine as well. DigitalOcean, again, the free stuff there. So it's always running fine. I even tried to run it on my Raspberry Pi, which again, it was working, but it was very slow. The response times were over a second, which was not acceptable to us. What we wanted to do is we wanted to improve on this because our goals were much higher. We wanted to do a system where we can enable, we can allow people to send in a lot more requests. So you can load test your systems by sending real HTTP traffic, web traffic to us. You wanted to make sure that we can log what's happening when you send in your request. We can give you real analytics on what's going on. So we wanted to consume and produce a lot more data to the integrators when it comes to these payment integrations. Because usually what happens when you do these integrations, you're sending in stuff into a black box and you have no idea what's gone wrong or what's gone right. We want to make sure that we shed some light to that black box and actually show you what you're doing and how we can be doing it. Okay? So the goal was this. The goal was to have a system where the minute you click a button or you send in your requests from your own systems, we show you how many requests you've done so far, what is your response coverage of the available different errors and successes, how much you covered so far within your tests. And we went a bit extra as well. We wanted to show you the exact things as they're happening on the server, serving it back to you in your browser. So the minute you hit a request, you get immediate feedback. So you can monitor your own progress, you can monitor your integration as you're doing it. Okay? And in order to do that, we had to revise our very simplistic infrastructure when it comes to the URL nodes themselves. So this is what we ended up with doing. So we had on the very top side, the URL virtual machine provides its own supervisors. Supervisors are main processes, main programs that the sole responsibility is looking after other programs. They call themselves children. And here you might hear me talking about children and dying. This is in the terms of processes, not anything extreme. So we ended up having a couple of processes that has single responsibilities that it was doing. So we had, for example, a reporting worker. So this was reporting back to us of all the happenings, all the events that triggered from a single HTTP request. We had a web worker, or a couple of web workers, which were responsible for accepting incoming traffic. And we wanted to make sure that we can handle hundreds of requests
Again, still staying on the tiny machines. Okay. We had something called redirect workers, so some of these payment examples or payment integrations would include you being redirected off to a third-party site. In Europe, it's quite common to have something called a 3D secure site or a Visa verified by Visa site. You have to go in and provide some arbitrary details about yourself to approve a transaction the first time or subsequently, depends on the provider. So to track those kind of happenings differently. In terms of other supervisors, so we have a request supervisors, every single time someone hit our services, we spawned off a single process. So every request had its own process. And the process was living as long as your request got through our systems, make sure that we have all the logs and all the events logged first. And after that, the process is chucked away, thrown away, the resources to be reused
for the next thing. Within the Erlang ecosystem, these processes are very cheap. They don't cost much. They're not like Java threads or threads or processes on other kind of languages. The Erlang virtual machine is a small virtual machine inside your physical or other virtual box, and it manages its own resources. And in terms of logs as well, so we wanted to split the logs. Every event we did, we wanted to split the logs. Just going back to this picture, the customer logs are these things. They got channeled through back to the browser as they happen. But they wanted to make sure that we keep a log of all these happenings internally to us, making sure that should something bad happen, we can go back and check exactly what happened, or which server it happened, what process triggered it, why stuff gone bad. So with this revised architecture, we managed to achieve load or response times under 20 milliseconds, still running on the smallest possible instances. We again managed to reach about 100 requests per second, which was a major improvement from about 5 to 10 in the previous setup. And we can handle about 70 under load, under heavy load, which meant, sending thousands of requests at the same time. It still can chuck through 70, 80 per second and serve that back to the customers. Okay, here's some graph as well about the progress. So what we did is we measured every single time we did some improvements in our architecture. We wanted to make sure that we measure the improvement and see if we actually did improve or regressed with these changes. So this is where we started. We could handle nearly 5 to 10 requests altogether, about 200 milliseconds per response time, and all these changes that we did to this architecture ended up here. We managed to bring up the number of requests we can serve, and then significantly bring down the request time in terms of processes that we've done. And just to have a nice comparison against my own Raspberry Pi, I wanted to run the same Raspberry Pi. I wanted to run the improved system as well, and I could even have respond 20 requests per second in the tiny machine, which is a better performance than our initial architecture on the bigger kind of AWS instances. Okay. I talked about Erlang as well, but we use Elixir exclusively as well for our message passing and reporting. So every single time the event processing is happening in Elixir, the API requests are handled in our Erlang nodes. And just going back to the pictures here, so everything all the counters, these percentage calculations, and these live logs are going through our Elixir nodes. The actual HTTP traffic or TCP traffic, depending on the API type, would go through our Erlang nodes. So I talked about supervisors before, but what are supervisors? So supervisors are these processes that today's single responsibility is the other processes they watch. All right, the other kind of resources they're responsible for. So supervisors have a built-in mechanism to deal with these children processes in many ways. So the first thing you have to choose when you're dealing within the Erlang ecosystem with the supervisors is the strategy, and this is important when you're expecting your load going up or down, or you're architecting your system within this ecosystem to the anticipated load or the anticipated usage that you do. And I'm going to talk about these strategies in detail in a few minutes. But I'll explain why one or the other is good for certain cases. The first thing you do is choose your strategy. Then there's two things which are very superfluous names called intensity and period. So in the Erlang ecosystem, you can set up, you can configure your processes, you can configure your programs to different restart strategies. If something bad happened within that process, that's always isolated. But whatever you sent to that process previously, whatever data it had before, it's still contained. And the process can restart based on their supervisor configuration, but it can be restarted with the same, at the time when the data processing stopped. And you don't lose anything, you don't lose data, you don't lose any of the events that happened. But what's important here is sometimes you end up in a situation where the process cannot be restarted, so you need to configure these supervisors to stop at certain time with these restarts. Intensity here would mean the number of restarts that will attempt to these processes, and period is the set period of time it will try these restarts at. So for example, if I have a process that is set to be restarted 20 times within 2 seconds, if it fails that criteria, it cannot be restarted either 20 times or within 2 seconds. The supervisor will send up a shutdown message to the Erlang virtual machine to go, I can't deal with this, you have to go in and manually fix it. Otherwise it will try to correct itself on its own within these boundaries, within these configurations. Okay? So the supervisors talk about, these are like the parent processes, they call them. The child processes will have a bit more identity, let's say. So for example, it has its own ID or name depending on the version of Erlang or the virtual machine you have. So you can refer these processes by name or ID. You can send messages to these things. Going back to here, for example, so these things would have its own name, own ID, so I can send messages to these processes and let them consume their own message queue as things happen and the things I send to them. The start defines the function that the starting parameters for the process, what it would need to do in order to get it up and running. The restart is when something goes wrong. What should I do with the current state of that process, the internals of that process now, and what do I have to do with that set of data or that queue of messages in order to start again or start consuming again that queue of messages or that data that I have. We have shutdown, which is, again, if something goes wrong with that process, I can still dump out that data, I can still salvage that flow of events and put it somewhere else, either put it in a database, either relational or NoSQL database, or just write it to a file and then I can consume it later as I fix the code after some times. Okay, so going back to the supervisor strategies, so this is the key thing here. There's the first strategy, which is the default one, is called 1-for-1. This is a good strategy when you have a fairly independent things consuming your requests or consuming your incoming events or processing data. So I have one worker that's producing image processing, another worker is producing logs based on some sort of an event, and so on and so on. If I apply this strategy called 1-for-1 for this kind of process tree, what happens if one of the workers gone away, something bad happened, the rest of my processes are independently working. They're not affected by this change at all. There's no there's no dependency between these processes whatsoever. So I can independently restart the failed process, no problem. Okay, so this is great. For example, when you have an API that serves different endpoints, different purposes, and if you run it under a single virtual machine, so a single Erlang virtual machine, if one of those APIs produces an error, the rest of them are unaffected. The rest of the endpoints are unaffected. They can still serve the traffic, no problem. Okay. There's another strategy called one for all. This will be used or commonly used for cases when these processes, these programs are heavily dependent on each other and they have to be started in order. Otherwise, your program won't function correctly. So for example, if you have a worker that is responsible for database entries and database gets, the other one is depending on those database entries and database lookups, and the third one is depending on these, whatever this worker 2 produced in terms of, transform that data from the database and send it over to worker 3 and worker 4 and so on. In this case, if one of the middle one fails, the other 2 won't function correctly. The other 2 will fault as well. So in this case, for example, if any of them fails, the supervisor will do is shut down all 4 all in one and then restart them in order again. So in this case, it will ensure that the system's integrity carries on after the error. The system's integrity is intact from the outside point of view, from your request point of view. Okay. There's another strategy as well, a RESTful one. Here, again, it's important that these things are linked, but not so heavily linked. So the previous item, there was a very heavy dependency. Here, it's a more looser dependency, but it's still some dependency between the workers, between these processes. It's, for example, if the second one dies, what it will do is it will kill or restart the other ones as well that came after the second one, and then they start them in order, making sure that again the integrity of the system is intact. Okay, and there's a fourth strategy when it comes to these data processing that's fairly new in the Erlang ecosystem, which is called simple one-for-one. So all these previous strategies would have to be declared, all the configuration had to be declared at startup time of your whole application. So you cannot change that sort of thing. If you encounter, for example, heavy load coming into your system, you can see these processes failing, you would have to shut it down and reconfigure it and start it up again. So there's manual intervention and potentially there is disturbance in your service that you provide to your customers. So to counter that, there's this strategy called the simple one-for-one, where during runtime you can start these different kind of processes as the load comes into your system, and as the load winds down, you can get rid of these processes as they come and go. There's no real limit to how many processes you can create in these kind of scenarios. What's important is they're still managed by a supervisor, a master process that helps you manage all these worker processes. So for example, in our case, we use this sort of strategy for every request. We use this whenever someone sends an API request to us, there's a process dedicated to that HTTP call or TCP call, and it lives on until it processes every single event, every single outcome from that HTTP call. After that, it's chucked away. In this case, we're not limited to, let's go back to some of the previous ones, we're not limited to a case where I have, let's say, 2 workers only processing my incoming requests, and it can pile up. If I send in 100 requests, 50 can pile up here, and 50 can pile up here, and there's so much these 2 can process and go through in order to serve back the desired responses, or serve back or register the desired events. that I'm looking for, the customer's looking for. In this case, if I have 100 requests coming into my system, I can easily scale up to 100 processes concurrently serving back the traffic, and then whenever they finish, they just go away, and the resources that are managing these processes, the CPU, the memory, will be freed up again for the next incoming request. Okay, and just to talk about budgets as well. So previously, the very early part of these slides, I was talking about budget. So we started off with, spending a year and a half going on and off working on this, and literally spending zero money possible in terms of servers, and managed to do so until about for about 8 months. And after that, as I go, just going back to the slides, we're talking about the very initial versions. So the very initial version was working fine, no problem, having on the free machines, but we were a bit more ambitious. We wanted to make sure that we can productize this idea, we can productize these APIs to a degree where we can serve back much higher load, much higher traffic, produce much higher intelligence back to our customers when it comes to our services. And when we got to the improved stage of our architecture, we ended up still running on AWS tiny machines or small machines. Our monthly bills were around under €100 a month just to serve back hundreds of requests per second. Usually you wouldn't see that in other commercial kind of businesses, where helping out another company at the moment where they have a big Java architecture, racking up lots of money in terms of bills just to serve back a tiny fraction of this traffic that we're trying to do here. And the key to that pretty much is choosing the right kind of technology for the right kind of tools. So we chose Erlang and Elixir for its own reason, for the reason that it's very efficient running on either small systems or big systems. So you can run the exact same code, the exact same program. You can run it on a Raspberry Pi, and then you can put it on a big machine with 8 cores and 4 terabytes of memory. It will still run the same program, just allows you to scale and serve a lot more traffic with the resources. The actual virtual machine is very efficient doing that. So you can even configure the virtual machine when you bring it into these big kind of systems, how many cores it will consume, how much memory it will consume. So you can still play with that. And it allowed us to do a thing where we can run our core service, the core product, on a very, very low budget, really. And in case we want to scale up, or our customers needs us to scale up because they send in a lot more requests as we grow and they grow, we can still do that, but just additionally just tweaking these machines, or just adding a bit more cores, two or four more cores, or a bit more memory, but without changing much of the architecture, changing any of the code, really. All it is just the server that it's running on. Everything else stays the same. And that's for us, that was proven one of the things that we really liked these technologies, and helped us to deliver a prototype and then turn the prototype into a product on a very, very low budget when it comes to the servers. And in terms of the talk, just going back there. And that's all I had to say today for this talk. I'm happy to answer the questions if you have any questions. All right, so first question, what about scalability of the system? Does the use of more powerful environment give the expected increasing of performance? Yes, it does. So the Erlang the virtual machine is, some call it greedy, but I think it's just very efficient. If you give it a lot more power, if you give it a lot more resources, it will just hungrily take it and use it to its own advantage and serve back a lot more. So it does give us the increase in performance. Yes, there's other tweaks we can use with the Erlang nodes as such. You can easily create distributed systems of these nodes, so you can connect these nodes up. That allows you to serve a lot more traffic as well, or you can dedicate nodes to serve certain type of applications. So one node for event logs, the other node is for counters, the third node is really just HTTP processing and responding back with whatever the format of the API requires, it's JSON or XML or just simple HTTP parameters. And during scaling, you could want to replace DB. How would you handle the difference in SQL syntax? So in these things, in Erlang Elixir, so there's libraries that allows you to, they're agnostic to your database layer as such. So you're not really restricted in what kind of database you're running underneath. They wouldn't be full ORMs like in other systems in Ruby or in Hibernate, I think in Java. So it wouldn't be that fully functional ORMs, but you can still do this sort of stuff very easily within this ecosystem. There's lots of libraries that help you doing these database connections. What amount of data are we talking about? So right now we have what was it last time? So we have hundreds of customers at the moment producing thousands of requests a week. So for every request we produce analytics and events in terms of megabytes every event. So it's for every request we produce about a couple of hundred megabytes of sort of stuff, whether it's logs for internal cases, data for our graphing, and so on. So it's big data in a sense. It's big as much as our customer base is big at the moment, but it allows us, this sort of system allows us to scale up in a much greater data consuming in case our customer base grows. This won't limit us in terms of that. We don't need to introduce new kind of measures in terms of processing these events. Okay. Anything else? All right. Thank you very much.